Hi again, everybody. Welcome back. So, this chapter on rotational kinematics. So far, we've talked about linear values like velocity, displacement, and acceleration, and equated them with angular values like angular displacement and angular velocity and angular acceleration, and have learned how to convert those. And we also talked about how accelerations, you can have either one type of acceleration, excuse me, or two types of acceleration on an object that is moving in a circle. If you recall, and in fact, I'm going to shrink this down a little bit because I don't feel like dealing with this lack of space right here. I'm going to shrink this down here. If you recall, in our uniform circular motion chapter, we had objects moving in a circular path. But the reason it was called uniform circular motion was because there was only centripetal acceleration. All right, so in order for an object to move, to be changing its direction, it must have an acceleration. All right, but we also just stated in the last segment of these notes, there may also be a tangential acceleration. So if we have an object moving in a circle, try to draw it in the same size, it definitely has centripetal acceleration. But if it is accelerating also in the tangential direction, so going faster and faster and faster and faster and faster around that circle, it also has what we call tangential acceleration. Of course, we equated that to being the radius times the rotational acceleration. But the point is that any object that is experiencing both these accelerations is going to have a combination of accelerations acting on them, and always acting at right angles to each other. Because if centripetal acceleration is always towards the center, there's a center right here, and if tangential acceleration is always at right angles, tangent to the edge of the circle, these are always going to be at right angles to each other, tangential and centripetal. So to get the total acceleration, the total acceleration that object is experiencing, it would be, and this should look familiar to you, your tangential acceleration squared plus your centripetal acceleration squared. Where does that come from? Well, that's simply the Pythagorean, right? Our Pythagorean theorem. So let's draw this in purple. So that means that this object is experiencing an inward acceleration and a tangential acceleration. So whatever the resultant of those would be right there, that would be your actual acceleration that this object is experiencing. Some towards the center, some tangential, but this is the total, you might say, the resultant or the magnitude of the acceleration. It also occurs at some sort of angle, right? What is the angle right here? Well, this angle, and I should draw this in a little bit bigger like that. This angle, here, we're going to call phi, or you could call it theta if you want. I know we called phi something else in our work and energy chapter, but this is not exactly theta, because theta was an angle that was measured from the x-axis. I'll make this a little bit bigger, I think. All right, we call this phi because it's measured from the tangential direction. All right, so if this is a tangential direction right here at any one point, this angle phi, which, look at it, it's the centripetal acceleration, it's the inverse tangent of the centripetal acceleration of the tangential acceleration. It's very much like saying it's the inverse tangent of the y over the x, right, or the rise over the run. So that gives us this angle right here. So we find the resultant acceleration, or the magnitude of the acceleration, by combining the centripetal and tangential in the same way that we did the x and y in our vectors chapter. And we find the angle the same way we did as before. The angle, our angle theta, well, I meant to draw it in black, but I don't care, I'll just keep it in red, of the acceleration is going to be the inverse tangent of the inward direction, that's centripetal acceleration, over the tangential direction, which is a sub t. Okay? So this brings us now to our first example, which we're going to do, and that's going to be the end of this segment right here. All right, that's going to be the example 10.8. Example 10.8. So, you may remember that I mentioned in the previous segment that centrifuges are used for, well, people like astronauts and so forth to experience various different forces and accelerations of gravity. But centrifuges are also used for medicinal purposes. All right. I want to give a try at this. A microhematocrit, I want to say, microhematocrit centrifuge. Now, hema, anything, deals with blood, right? Like hemoglobin and that kind of thing. So we've got blood in this centrifuge, and they're placed, should be a D there, they're placed in little tubes, kind of like that thing that you saw in the previous picture in the previous segment. All right? There's little plastic vials right there. So I'm going to draw a tube, let's see. Now they look like little pointy things. I'm going to draw it, and that's bad already. I'm going to draw it just like a test tube. All right, like that. And so right here is the center. And these things are kind of rotated around. Oops, I can't quite get. You guys can't see, but there's a menu bar over here I can't get to. Like so, all right, and as this thing whirls around, of course, centripetal forces cause the blood to kind of go to the very bottom of the tubes, all right, and they experience all the forces that you're doing the tests for. Okay, there, and so forth. All right, so let's write down some things that we know about this. First of all, RPMs, 11,500 RPM. Well, that is 11,500 revolutions per minute, right? First thing we want to do is we want to convert that to radians per second, right? Well, equals, I'm going to multiply. 1 revolution equals 2 pi radians. All right, sorry, that pi is kind of messed up. And of course, 1 minute equals 60 seconds. So that's going to give us a number of radians per second. Let's just do that right off the bat. All right, and with our answer, I found that I've run out of space. So let's do this. Give myself a little more space there. There we go. 1204, 1,204 radians per second. Okay, good. So that is our angular velocity. Angular velocity. Let's see, the bottoms of the tubes. All right, so that means that this bottom of this tube here, and this guy over here is 9.07 centimeters from the axis of rotation. So if we draw, so this is our so we're rotating positively, which is counterclockwise. So that's the very bottom of the tube right there, and that radius, that distance right there, is 9.07 centimeters. Well, we know we don't want to stay in centimeters. We want that to be, it's our radius. And so our radius is going to be 9.07 centimeters. Let's convert that to meters. So 100 centimeters equals 1 meter. That's going to give us 0.0907 meters. Okay, there's our radius. Number 1, we want to find the linear speed of the bottom of the tubes. Linear speed of the bottom of the tubes. Okay, so A, simply our velocity. All right, what would the speed of these be if it were to shoot off in a straight line? All right, the linear speed, the linear velocity, what would that be? All right, well, we know from our segment before, that we have a relationship between linear speed and angular speed, and that's by the radius. We say the linear speed is radius times the angular speed, right there, our angular velocity. All right, so let's just put our values in, because we have both of those right there. So that's 0.090, oops, too many zeros, 07 meters times 1,204 radians per second. All right. Oh, you know, I didn't put the meters in the first one. No, that's all right. All right, let's punch our numbers and see what we get. I get 109. What? That's meters per second. Meters per second. Imagine that. 100. So that's over a football field. That's well over a football field in 1 second. So these things are moving tremendously fast. And in fact, lab centrifuges are known for being very, very, very high velocity. Okay? So, well, and if you think about that, 11,000 revolutions per minute, that's a lot of revolutions in a fairly short amount of time. So that should stand to reason that it's going to have a very, very high linear velocity. Let's now find our centripetal acceleration. Part B asks us centripetal acceleration. What's that going to be? Well, once again, we said in the last segment that our equation for centripetal acceleration, actually I'm going to write this down in the lower left-hand corner. We said that centripetal acceleration in uniform circular motion was v squared over r, right? Well, if we took our v and squared that, would be r squared over omega squared, and if we took that over r, simply our centripetal acceleration would shake out to be r omega squared. All right, r omega squared. So let's just put our values in and see what we get. Once again, our radius is 0.0907 meters, and our our rotational acceleration is 1,204 radians per second. You know what? I'm going to leave the units out just because. Radians per second. We know that that is the centripetal acceleration, or the centripetal velocity. But remember, it has to be squared, right? It's got to be squared right there. That's going to make a big difference. So hopefully these things are pretty well built, because there's going to be a huge centripetal acceleration applied by these on the blood at the very bottoms of the tubes right there. What do we get? Wow, this is a big number. 100, in fact, I'm going to put it in scientific notation because it's just way too big. 1.31 times 10 to the, 5 times 10 to the 5th meters per second squared. Meters per second squared. Now, it's not radians per second squared. It's not rotational acceleration. It's actually centripetal acceleration being directed towards the center right there. So what would that acceleration be? 1.31 times 10 to the 5th meters per second squared. 131,000 meters per second squared. So a very, very high acceleration applied to the blood in the bottoms of these tubes right here, and they need that to be able to determine how blood behaves in those conditions. Quite honestly, I don't I don't really know why they do that, but they need to subject that blood to those forces and to those accelerations. So that's example 10.8. I'm going to stop for right there. We're at about 13 minutes already, so I'll give you a break, but we're going to come back in the next segment and do example 10.9. Make sure if you have any questions to ask me. And in the meantime, thanks for watching, and I'll see you on the next one.